Yesterday we looked at two things before we dropped our eggs. The first thing was the whole qualitative nature of impulse. The quantitative nature we're good at. It's just problems, right? Plugging numbers into an equation, not so bad. All stems, though, the qualitative nature from that equation, F times delta t. Impulse is F times delta t. First situation, we're stopping an object, right? Something's moving, we're trying to stop it. Okay? That's a predetermined impulse. That's an impulse that we don't affect whatsoever. It's going to be the same no matter how the object comes to a stop. When we have a predetermined impulse, usually the idea is that we want to increase the time that it takes to stop the object. Now, that may be from an airbag, increases the time that it takes your head to stop. It may be from the goalie pad, the time that it takes the puck to stop. Okay, it may be the crumple zone in the car, increasing the time that it takes the car to stop. Whatever it is that cushions an impact, that stops an object but increases the stopping time, the purpose of it is to do what? Increase the stopping time so we decrease the force. Yeah, again, time goes up, force goes down. Now, there are exceptions to that. There is possibly that situation where we want to decrease the stopping time, increase the force. That is, if we want to break something, right? Okay, but usually it's the other way around. We're usually trying to decrease the force by increasing the stopping time. All right, the other situation is when we're trying to start something. We're trying to make something go faster, give it more momentum, give it more impulse. That's when we have what I call a non-predetermined impulse. Here, if we increase the force, what happens? We're not doing anything to the time, are we? If we increase the force, we're going to increase the impulse. If we increase the time of contact between the stick and the puck, between the ball and the hand, okay, between whatever and whatever, if we increase the time, we're also going to increase the impulse. So again, be careful. When we have the predetermined impulse, time affects force. When we don't have a predetermined impulse, time affects impulse, and force also affects impulse. Okay? So yesterday you saw a couple videos, right? The Phil Kessel, the hockey player, taking the wrist shot. Okay, we saw the flex in his stick. Okay, the flex in his stick increased the time of contact. That didn't decrease the force because he was starting the object. It increased the impulse, made the puck go faster. The other video was when the Cirque du Soleil people were getting flipped off of this teeter-totter and going up 30 feet in the air and then coming back down onto this mat. Four guys were holding the mat, and as the guy hit the mat, as he was coming down and they hit the mat, they dropped the mat. Okay? The reason for that was to increase the time, but this time, increasing the time decreased the force, didn't increase the impulse. Okay? Now, the other thing we looked at yesterday was that force versus time graph. That force versus time graph, which typically is going to be a straight line for us, or multiple straight lines. It might look something like this. But in the end, we're not going to have curved lines here. Bailey, what do you think as soon as you see this force versus time graph? 3 words. Good. Area equals impulse. Every single time. It doesn't matter if you're asked for impulse. This is what you should think. Area equals impulse. Got it? Now, sometimes you may need to go a little bit further than that. Sometimes you may need to find a final velocity or a change in velocity. If that's the case, then let's get the area, which equals the impulse, and then set that impulse equal to m times delta t. Why do we not want to set impulse equal to f times delta t here? What's the problem with that one? Okay, this one's just fine. This one, not so good. What's wrong with that one? I talked about this a little bit yesterday. Yeah, what force do you use, right? What force do you use? The force is changing the whole way through this problem here. What value of force do you use? Now, technically, you could use the average value of the force there and make that work, but what's the average value of the force on that graph, right? Okay, it's unless it's a nice straight horizontal line, it becomes a lot more difficult to use that force. So just don't even try. Okay, don't even try. Delta P is equal to m times delta P. All right, we had 3 questions for homework last night. 2 of them on page 462, and then 1 of them was question number 9 on worksheet number 2. Let's take a look at these ones first. Any issues with either of these questions on page 462, please? Daniel? 2C? Any others? 1C? 2C and 1C. All right. Number 1 involved, you know what, I think we're going to have to do the whole questions actually in order to do C. That's okay though. Number 1 says, draw a graph of the net force as a function of time for a 0.65 kilogram basketball being shot. Okay, force, this is question number 1, force versus time. During the first 0.15 seconds, it increases from 0 to 22 newtons, the force. So let's make that 22 newtons, 0.15 seconds. During the next 0.25 seconds, it decreases linearly to 0. So what's this time going to be over here? 0.25? 0.4, good. 0.25 seconds later, it's going to decrease like this. Okay? Good, I think. I think that's it. Now, as soon as we see that graph, we think area equals impulse, even if we're not asked to solve for question B, or even if we're to go straight to C, we're still going to have to do area equals impulse. So let's do that. A is equal to delta P, or impulse, and that's equal to, in this case, it's 1/2 base times height. A couple of times I've done this over the years, just silly little, you know, kind of brain freezes, brain not working very well. See something like this, and I break it up into 2 right-angled triangles, and then I do 1/2 base times height, 1/2 base times height, and then I add them together. Is that necessary? It's right, and it's not wrong, but it doesn't matter if you have a right-angled triangle when you're using 1/2 base times height, right? It does if you're using sine, cos, or tan, but 1/2 base times height works whether it's right angle or not. So there's no reason why I can't just do this in one step. The base is 0.4, the height is 22. We do the math there, and it should work out to be 4.4 Newton seconds, or 4.4. What are the other units that you could use there? Good, kilograms, meters per second, good. Now, I want to find the speed of the ball when it leaves the shooter's hands. Okay, you guys know roughly how to do this. We know that delta P is equal to m times delta V. We're not going to use F times T here, okay, because the force isn't constant. It's a changing force. So let's use m times delta V. We know what delta P is. It's 4.4. We know what the mass is. It's 0.650. We can solve for delta V. 4.4 divided by 0.65 gives me delta V, I assume, equal to 6.8 meters per second. Now, technically, I've just found delta V, and I was looking for VF, right? How fast is this ball moving before it's shot? Presumably not at all, right? So VI would be 0. If you get delta V equal to 6.8 and VI is 0, then what's VF going to be? Which is really what we're looking for here, 6.8. All right, similar question number 2. We got to draw a graph of this one as well. It says the force is 21 newtons west for 0.12 seconds. We're going to make the force here in newtons to the west so that we can still do it above the x-axis. If we did have a line below the x-axis, how would it change things? Caitlin, how would it change things? We're going to make a negative, right? Area still equals impulse, but we're going to make it a negative impulse in that case. You know what? We're just going to define west as positive, and then our graph is above the x-axis. We don't have to worry about the negative then, okay? So it's 21 newtons west for 0.12 seconds. This is time, 0.12 seconds, 21 newtons. That's it, isn't it? Straight, flat, horizontal line. What's the impulse? Well, area equals impulse. Let's say this time it's going to be base times height. The base is 0.12. The height is 21. I don't know what the answer is there. Scroll down a little bit. 2.5. And it's going to be to the west, since we defined west as positive. What could you have done there in this question besides calculating the area? We could have used delta P is equal to F times T in this case, right? Why? Why would that have been okay here to find the impulse? Right, the force is constant. Okay, when that force isn't changing, F times T works just fine. But in the end, if you multiply F times T, really what are you doing? You're multiplying the height times the base, which is the area, right? It's exactly the same thing. So it doesn't really matter in that case. You know what? I'd stick with the area, and that way we're thinking the same way every time we see the question, okay? C, the impulse changes the velocity from 4 to 2. Oh, look at that. Changing direction here. Let's get at our ugly highlighter here. Okay, because all of you guys did that last night, right? Went to the ugly highlighter store to buy the ugliest color highlighter you can to draw attention to things like that. Okay, the fact that the direction is changing from the east, Devon, to the west. Okay, something's got to be negative here. What's the mass of the ball? Oh, we haven't solved for mass of the ball in any of these questions yet. That's okay. We know what to do next. Delta P is equal to M times delta V. We know what delta P is. It's 2.5. We're looking for M. What's delta V? Well, it's going from 4 to 2 to the west. So we're going to say final, -2, minus, and no, wait. Oh, wait. Wait. What did we define as positive? West, right? So it's going to be final is +2. A little bit odd here, right? Okay, this is positive. This is negative because up here we defined west as positive. That make sense? Okay. If we wanted to make west negative down here, we would have had to make that a -2.5 because it would have been below the x-axis. 2 minus -4. 2.5 divided by 6. Should be 0.42 kilograms. Good. Listen, if you didn't catch that whole negative thing with the east and positive with the west there on the bottom, what would you have gotten for an answer? -0.42 kilograms, right? Well, you know that's not the right answer, right? You know it can't be a negative mass. Okay, odds are it's just the flip of that. So you probably would have gotten away with it. We just don't want to take that chance. All right, one more question. That was question number 9 on worksheet number 2. Just like the questions we just did, except we don't have to actually have to plot the graph. The impulse experienced by a 4-kilogram object represented in the graph below, the object's change in velocity. Devin, what are the 3 words you think of when you see that graph? Good, area equals impulse. I don't care what you're asked, let's get area equals impulse. Area equals impulse. And the area of this, because it's a triangle, is going to be 1/2 base times height. So the base is 10, the height is 4. If this was below the x-axis, what would we do with it again, Simon? We'd make it a negative, right? If you had some above, some below, calculate the area above, calculate the area below, and then just add them together, making sure you make the one below a negative value. 1/2 of 10 times 4 is going to give me 20 Newton seconds, or 20 kilograms meters per second. The change in velocity, delta P is equal to what? It's equal to F times T. Can't use that because it's a changing force. So what am I going to set it equal to there? Caitlin? Good, M times delta V. Okay, be really careful about that. Caitlin, I think you probably meant what was right here. Okay, but be very, very careful about the way you're thinking of it and saying it. Caitlin said M times V. Okay. If she's thinking the right thing and writes down the right thing, that's great. But the danger is we'll write down M times V. That's wrong. Okay, it's not MV. Okay, that's momentum. We're talking about impulse here, M times delta V. Now, If VI is 0, then VF will be the change in velocity. But if VI isn't 0, and we don't know that here, okay, then VF wouldn't be the change in velocity. Does that make sense? So we got to be really, really careful with that. Solving for delta V, delta P over M. We got 20 over 4.0. Delta V is going to be equal to 5.0 meters per second. As I was walking around checking to see who had this done a few minutes ago, I saw a lot of 5s. Okay, so it doesn't look like we had too much trouble with this. We're good? Let's try one more little question here. I'm giving you the impulse in this question, 25 Newton seconds, and I'm giving you the shape of the graph. I'm asking you in this question, what's the maximum force? Force is changing, right? It's not the same value all the way through, but what's the maximum force? Okay, I'm going to start you off with 3 words, and then I'm going to see what you can do for the next 1 or 2 minutes on this question. Okay, 3 words are area equals impulse. I still want you to think that. Okay, just because you're looking at a question that's asking for a different variable this time, and just because you can't calculate the area because you don't know what the y-axis is, you're still thinking area equals impulse every single time. Okay, let's go at it, see what we can do over the next minute or so. All right, let's see what we got here. First thing that we said was think area equals impulse. My problem with thinking area equals impulse here is that I can't actually calculate the impulse because I don't know what the y-axis is. I don't know what the value for the y-axis is. So how do I think area equals impulse? How does that make life easier for me if I think that way in this question when I can't actually calculate it? Okay, so impulse is equal to 1/2 base times height. My problem is I don't know what the height is though, right? So where's my solution there? Yeah, Maria? Good. I know the base. So let's plug that in. The base is 5 in this case, right? We don't know what the height is, okay, but it's something at least. Well, how do I calculate 1/2 of 5 times something? Yeah, Maddie? Good. I don't have to calculate 1/2 of 5 times something. I know the impulse already. I know the area. Look, I'm told what the area is. We still think area equals impulse, but I don't have to calculate the area this time. I'm going to use the area this time. It's 25. So we're going to take the half over by multiplying by 2. It becomes 50. 50 divided by 5 is 10. The height of this is 10. So what use is that? Maria? Yeah, that's my answer, right? The height of this graph is my maximum force. And that's going to be newtons, right? Because the y-axis is measured in newtons. How many people got 10 newtons for that? Good. Very good. Yep. I used 5 because the whole base is 5, right? We go from 0 to 2 right here to 5 over here, right? It's good? All right. Here's some homework for tonight, guys. Page 467, number 1 to 13. We'll do a couple multiple choice questions right now. Then we're going to show you a couple little videos and go on to a new concept here. All right, I want to do 2 multiple choice questions here. First one is question number 7. This appears in the worksheet booklet that I gave you at the beginning of the year at the end of Unit 1. All right, everyone, let's take a look at the responses here. Most people, more than 2/3 of you guys, said the answer was C. 11% said A. 22% said E. I'm not sure how to do this. Okay, the answer is C. So thankfully, most of you were correct. Let's go through why the answer is C here, though. You guys have all had a chance to read the question. It says, foundation piles for tall buildings are hammered into the ground using a pile driver. A pile driver similar to the one shown below lifts a 900-kilogram hammer a distance of 3.5 meters above the top of a pile and then allows it to drop. You guys have seen this before. When they're building a building, okay, they do this. Like a big building, that is. They'll do this. When they're building a bridge, they'll do this. They literally drive piles, just pieces of steel, into the ground. And then they leave them there. What's the point of that? Well, sometimes they call them friction piles. As these piles go down into the ground further and further and further, they displace more and more and more soil. So as they displace more soil, there's more force acting back in on these steel piles, which creates more and more friction. So the idea is that the further you drive them into the ground, the more friction there is on these piles, and the less likely they are to go further down into the ground. What's the point of that? Build a bridge on top of it. The bridge doesn't sink down into the ground because it's got these friction piles that's holding the bridge up, basically, or holding the building up. Okay, so whenever you're on the side of the highway and they're building a bridge and you see this hammer coming down, bang, then they lift it back up, bang, then they lift it back up, bang, and they keep driving in a few inches every time, that's what they're doing. They're trying to provide a good solid base for the bridge or the building or whatever it is they're trying to build. We want to find the impulse, the magnitude of the impulse delivered by the hammer to the pile. The hammer to the pile. All right. Well, we know that impulse is equal to delta P, and we know that impulse is equal to F times T and M times delta V as well. We know that we've got a mass up here of 900 kilograms. We know that this pile is going to fall a distance of 3.5 meters, so the displacement would be technically negative 3.5 meters, right? The hammer falls 0.35 meters, or 3.5 meters. What are you going to use here to find impulse? F times T or M times delta V? I know? M times delta V, right? Not M times V. M times delta V. Sure. Let's give that a try. M times delta V. We know what M is. M is 900 kilograms. And in fact, we know what VI is. VI would be 0, right? Because it's moving, it's at rest before it's dropped. We have to find VF. And we've done this lots of times, actually. VF squared is equal to VI squared plus 2AD. So VF becomes the square root of 0 squared plus 2 times neg 9.81 as this hammer falls times the displacement of negative 3.5. Daniel, what'd you get for VF there? 8.28 meters per second. Thank you. Now, the final velocity of this hammer as it hits the ground, or as it hits the pile, I should say, is negative 8.28 meters per second. The initial velocity would be 0. 900 times negative 8.28 would be 7,460, right? Wait, that answer's not there, is it? Well, it is, actually. That's Newton seconds. Our final answers are measured in kilonewtons seconds. So 7.46 kilonewton seconds. Is that not the same as 7,460? It is. Right. Make sense? Good there, guys? The answer is for sure C. Let's do question number 8 here now. Don't bother submitting this one. Just do this one for the next 60 seconds, and then we'll take a look at it as a group. Time to take a look at this one. Number 8 says, the impulse from the last question is delivered by the pile driver in 2 times 10 to the negative 3 seconds. So the impulse is delivered to that pile in a very, very short period of time, 0.002 seconds. Basically 2 1,000ths of a second. The magnitude of the force that the hammer exerts on the pile, expressed in scientific notation, is what? Now, look at that. That time is very, very small. What would you predict that force to be if the time of contact is small when the pile driver is stopping? Usually we want to increase the stopping time, right? Here, we got a really, really small stopping time. What's that going to do to the force? Yeah? It's going to go way, way up, which is what we want, right? We're trying to drive this piece of steel into the ground. We want a big force. We don't want a little force here, okay? You can jump up and down on that thing. You're not going to move it at all because too small a force isn't going to do it. Listen, if a small force did something, then it wouldn't do a very good job at supporting the bridge, would it? Okay, we want a big force to drive it into the ground. Okay, we know the impulse was 7.46 times 10 to the 3 Newton seconds in the last question. We know the time here is 2.10 times 10 to the negative 3 seconds. And we want to find the force here. So pretty straightforward if we recognize all this. Delta P is equal to F times T, or F is equal to delta P over T. That's 7.46 times 10 to the 3 divided by 2.1 times 10 to the negative 3. And what's that work out to be? 7? $355,145. Anybody agree with that? Yes? Okay. That is a big number, but that's what we want, a big number, right? We're trying to drive the pile into the ground. We don't want some piddly little number that's not going to move this pile. Okay, the whole point of it is to hold things up. If it's going to hold up a heavy thing, it needs to have a big force driving into the ground. By the way, how are we going to express this? Some people would express this probably as a 3, just 3. Some people would express it probably as 4. We want the value of B. B is the base. We don't want the exponent here, just the base. But we want the base in 3 digits. So we're going to express this final answer. Okay, you guys have all seen a bubble sheet before, whether it was in Science 9 or some other diploma exam you've taken. 3.55. Okay? I'm telling you, the common mistake in this question is people will write either 3 or a 4 in the first box and leave it. Because they see this B times 10 to the W, we only want the value of B. Okay? The base doesn't have to be a single digit. Okay? Read the sentence after that. Record your 3-digit answer. They're telling you the value of B is 3 digits. It's simply something decimal something something, 3.55.